In this video, we're going to look at the reactions of monosaccharides. And the good news is, for the most part, you've already had every one of these reactions. Okay, so let's look at the first one here. Right, recall from a few weeks ago, or in summer school a few days ago, that you can take an aldehyde or ketone and reduce it with sodium borohydride or lithium aluminum hydride, and then work that up with water, and you'll convert the C double bond O into an alcohol group. All right. Now, most of our all the carbohydrates we've seen do have a C double bond O. Here's an aldehyde right here. Okay. And this aldehyde is perfectly susceptible to reaction with sodium borohydride, just like in the equation over to the left. We typically don't use lithium aluminum hydride because these are only soluble in very polar solvents that would be very reactive to lithium aluminum hydride. So it's really only safe to use sodium borohydride in these reactions. All right, so let's take this glucose as the compound that we have here. And we're going to react it with sodium borohydride and then water right here. And what you're going to find here is that the aldehyde group converts to a CH2OH group. All right, this type of compound where we've reduced the carbonyl group in a monosaccharide into the corresponding alcohol is called an alditol. And this one here is sorbitol. This is a sweetener that doesn't cause tooth decay, so you see it used in things like Trident chewing gum. All right. Okay. All right. You're probably saying to yourself, hey, glucose doesn't look like this. Glucose looks like this. It's a hemiacetal. It's a stable hemiacetal. Very little of it actually exists as this open chain aldehyde. Well, in aqueous solution at elevated temperature and with the acid base that the byproducts of this reaction generate, you're actually going to set up an equilibrium between the hemiacetal form and the open chain form here. So there's enough of this compound present for this reaction to go all the way to completion. Okay, so you don't have to have a lot of you don't have to have it in all this form. All you got to do is have some of it in this form, and even though this equilibrium here is indicated as being unfavorable, there's enough of this for the reaction to go to completion. Okay. All right, here's a common type of question you see associated with these sodium borohydride reductions. Upon treatment with sodium borohydride, which of the aldohexoses depicted give an optically inactive compound? Okay, so of course, all of these are going to end up having a lot of chiral centers. And how do we have an optically inactive compound when we have chiral centers? Of course, we're going to be looking for a meso compound. We're going to be looking for a compound that has a plane of symmetry. All right, so let's consider the reduction product of each of those. And what we find here is that only the compound on the far left, which is galactose, is going to give us a compound with a plane of symmetry. Okay, so when you draw this in its open chain form, actually the product you can only draw in the open chain form. There's a plane of symmetry right here going between carbons 3 and carbons 4 of the system. So this is the meso compound. Okay, when you reduce this one, you get a rotational axis of symmetry. You can rotate it around like that and get it back to what you have, but that's not chirality has to have a plane of symmetry. So we still have a plane of, we do not have a plane of symmetry. So we have a chiral molecule here at the bottom. So this one is chiral. Okay, a rotational axis doesn't do away with our chiral center. Okay, it's only when it has a plane of symmetry that it's meso. It can't have a rotational axis of symmetry. This one again also has a rotational axis but no plane of symmetry. This is not a plane of symmetry right here. Okay, so this one is also a chiral compound. Again, it has a rotational axis of symmetry but not a plane of symmetry. So we can't. So that is a chiral molecule, not superimposable on its mirror image. All right, so only the one on the left gives us an achiral meso compound upon sodium borohydride reduction. All right, we can oxidize carbohydrates too, but we have to be very careful about how we do that. All right, if you treat this with any form of chromium-6, you're going to get a violent exothermic reaction producing a lot of CO2, probably a few flames. So this is a way to burn a carbohydrate, but not really to do any sort of selective oxidation. Okay, using the milder reagents that we saw back in the aldehyde chapter, things that are very specific for oxidizing an aldehyde into a carboxylic acid. Those reagents here give us a mixture of carboxylic acid up here and give us a lot of the closed forms of oxidized products. So these are not very clean. These are actually used to test to see if we have free aldehyde groups in sugars, and we use these as a test for the presence of a free aldehyde or a potentially free aldehyde through its hemiacetal form. So we use this term reducing sugar to refer to a sugar that has a free aldehyde or a free hemiacetal group in it. Okay, and I'll try to point that out as we get to more complex carbohydrate systems. All right, so if you want to do a selective oxidation, the reagents of choice are either bromine and water, which gives you just all it does is convert the aldehyde hemiacetal group into a carboxylic acid, and this is called an aldonic acid. Okay, nitric acid is a little bit stronger, more vigorous of an oxidizing agent, and this gives us a carboxylic acid at both ends of the molecule and gives us an aldaric acid. Okay, so these are the selective clean oxidations that you can do on a carbohydrate molecule. Oxidize the aldehyde group to an acid with bromine water, or oxidize the aldehyde group and the alcohol on the end all the way to the oxidize both of those to two carboxylic acid groups using nitric acid. Okay, here's another reaction that's kind of an interesting phenomenon. Its name doesn't suggest that it's a reaction, but it is. This is called mutarotation, and it arises from the fact that people observing this reaction a hundred plus years ago, all they saw were changes in the specific in the optical rotation or in the specific rotation values. Okay, you can actually isolate alpha-D-glucose, and when it's not in water and it's at room temperature or below, it's actually stable in this configuration. It doesn't really convert to doesn't open to the open chain form. Okay, and alpha-D-glucose has a specific rotation value of 112.2. You can also isolate beta-D-glucose, and this rotation is 18.7 degrees. All right, notice that they're diastereomers, right? They're different at one chiral center, but not all. So the fact that they can have the same rotation value is there's nothing wrong with that. Okay, all right. Or the fact that they can have different rotation values. They're not equal but opposite is what I'm getting at. When you put these in water and you heat it, eventually either of those compounds is going to isomerize to this equilibrium mixture of alpha and beta anomers. Okay, so if you start with 100% D-glucose, alpha D-glucose, you get a 36 to 64 mixture that's mostly beta. If you start with pure beta D-glucose, you get a mixture that's also 36 to 64, mostly the beta form. Okay, the specific rotation that you'll observe is now 52.5 degrees, which is a weighted average reflecting that most of this is the beta form, and you see that it's closer to 18.7 than it is to 112.2. Okay, that's because there's more of the beta form. How does this interconversion happen? Okay, so MUTAROTATION is just a name for the interconversion of two anomers. All right, so what happens here is in water, we equilibrate with the open chain form. This equilibrium, actually I have it as an equal equilibrium. It's really heavily favoring the closed chain form. Okay, but there's enough of this generated. Okay, and once you generate this, you can rotate around that CC bond there, the one that I've shown in magenta. And when you rotate like so, you'll interconvert the position of the C double bond O and the H. And now if you close it again, you'll get to the beta D-glucose. And how beta D-glucose becomes alpha is just the reverse of this process. Okay? All right. So the MUTAROTATION happens because we go back to the open chain form, and the open chain form, remember, has the possibility to close in two different ways. Even though we start with the pure alpha, if we expose it to conditions that are going to interconvert the closed chain and the open chain forms, we're going to see the net result is that we're going to interconvert alpha and beta, and eventually an equilibrium is reached, and it's 36 to 64 in this case. All right. The two reactions that we're going to talk about now were very important in the early days of chemistry, because there was no spectral methods available to assign structures. Okay, so you had to do it the hard way. You had to look at chemical reactions that interconverted structures. And one of the important reactions is the Fischer-Killani chain extension. Okay, this is a very important reaction in the field of organic chemistry because it established the structures of all of the aldohexoses, aldopentoses, and aldotetroses. Okay, all right, so let's take D-erythrose right here. We're going to treat it with hydrogen cyanide, which usually we don't like to use this reagent as a gas, right? It's very toxic, so usually you'll see sodium cyanide, then H3O+. And this is, of course, cyanohydrin formation. Oh, sorry, I don't have to write it. I got it right there. Okay, all right, so we make the cyanohydrin. We're making it at this carbon right here, right? So that carbon now becomes this carbon. And note now that whereas this carbon in the starting material is sp2, it's sp3 here, and it has 4 different things attached. So this new stereocenter, we don't have any control over it, so we get both of the diastereomers, okay? All right, when we reduce this, we're going to reduce it in the presence of aqueous acid, and what happens here is that the nitrile, it's got to make the imine first. So once we make the imine, it's going to hydrolyze to the aldehyde. Okay? All right, so erythrose, if you expose it to this set of reactions, cyanohydrin formation followed by reduction and hydrolysis, you'll get a mixture of D-ribose and D-arabinose. Okay? And this is how the structure of these were solved. Okay? It was known that D-ribose and D-arabinose, they're both aldopentoses, but it's known that they're different only at carbon 2, right there, because they both can be prepared from D-erythrose. So that establishes that D-ribose and D-arabinose are different only at carbon 2. Okay, we can also reverse the Fischer-Killani chain extension. This is called the Wohl degradation, and there's another reaction that's just like it called the rough degradation. I'm going to present only the Wohl degradation because it's the exact reverse of the, or it's sort of the exact reverse of the Fischer-Killani chain extension. All right, so what we're going to do in the Wohl degradation is we're going to take our carbohydrate and we're going to treat it with hydroxylamine. Probably need a little bit of H plus in this process, and this is going to convert the aldehyde group into the oxy. Okay, we're now going to treat this with a large excess of acetic anhydride and pyridine, and this is going to turn every OH group into an acetate ester, including the OH group on nitrogen. Okay, so this is what we're going to get from this process. And now when we hydrolyze this, what you find here is that you're actually going to lose this carbon. Okay? All right, so this carbon is going to go away. Okay, it's going to go away as sodium cyanide. Okay, we'll look at that in just a second. So excess sodium methoxide is going to hydrolyze every one of these esters. And what it does initially, however, is it does kind of like an E2 reaction. Okay, so we're going to remove that and we'll make that. Remember that a cyanohydrin is not stable in base, so it's going to now eject hydrogen cyanide, and we're going to see that the chain is going to become shorter by one carbon. And what we note here is that D-ribose gave us D-erythrose, so we could prove in the opposite direction what we just proved in the forward direction, or we made it longer in the previous slide. Here we're making it shorter, so this is just added proof. And of course, we know that there's another aldopentose that would give D-erythrose. That's, of course, D-arabinose, because, again, they only differ at carbon 2, and carbon 2 is going to end up being a carbonyl group in the final product. Okay, in the book that we use, the Wohl degradation is not there, so I've given you a link to the Wikipedia article about the Wohl degradation, and that'll also show you another way to degrade carbohydrates using an oxidative procedure as well, but that basically tells you the same thing. That's called the rough degradation. All right. Another thing we can do is we can epimerize and isomerize carbohydrates. All right, so this proton here is simply alpha to a C double bond O, and therefore it's acidic. All right, so when you treat Glucose with aqueous KOH, you set up an equilibrium between the three compounds depicted, glucose, D-mannose, and D-fructose. How does this happen? Okay? All right, recognize that KOH could do a lot of things with this molecule. It could add to the carbonyl group. It could pull off a proton from any of the OH groups, but it's only by removing this proton right here that I've circled that you actually put this reaction in a forward direction. Okay, so what happens here is that we remove this alpha proton, and this gives us the enolate. Okay, we're going to protonate this, and when we add the proton here to this carbon, what we find here is that we can add it to either side. Okay, so this enolate reacting with water is going to give us a mixture of D-mannose and D-glucose. All right, another thing we can do is we can turn the enolate into the enol. Okay, and when we turn the enol back into a ketone, we can do it like we did over here and make mannose or glucose, but we can also, okay, and this one we probably need a little bit of acid. We'll just put that there. We can also add it that way, and this gives us the D-fructose. The carbonyl group is now at the 2 position, okay, instead of at the 1 position, and it's a ketone now, not an aldehyde. So this gives us D-fructose. All right, so you set up an equilibrium between all of these when you treat it with when you heat it in strong base like aqueous KOH. All right, another important reaction here is acetal formation. And we're not going to call it an acetal anymore. We're going to call it a glycoside, a glucose derivative, or a derivative of a sugar, okay? But that's a fancy name for an acetal, okay? All right, so when we treat a carbohydrate, in this case, I believe I'm using galactose, with acid and ethanol, we're using classic acetal formation conditions. Okay, we take only the anomeric carbon, and we take the OH at the anomeric carbon and convert it into an ether. Okay, since this ether here has 2 oxygens on 1 carbon, it's technically an acetal and not an ether. Okay, this reaction is very selective for this carbon. What happens here is that we protonate this, okay, get the protonated alcohol. Yeah, we eject water. This gives us the carbocation, but we can draw this resonance structure, the oxonium ion. Okay, let me just show you how that interconverts. Okay, so we got a couple of lone pairs there at oxygen, and we're just stabilizing the carbocation through that resonance interaction right there. We're going to add ethanol. Okay, I'll just show ethanol adding right here with arrows, and that gives us the protonated acetal. Okay, protonated acetal right here, and we just lose the extra proton to get the glycoside derivative. All right, you're probably thinking, I got a lot of OH groups here. Why this one? Well, it's only this one that gives you a stable carbocation. Let's just imagine that we're going to lose this OH group here. Okay? All right, so let's look at the carbocation that we get from that. Carbocation here doesn't have any resonance stabilization. It's just secondary carbocation. Better than primary, but not really all that good compared with one that has resonance stabilization by an oxygen atom. Okay? All right, so it's very easy to selectively turn the anomeric OH group into an OR group just by using acetal formation conditions, and only that OH group is touched under these conditions. All right, we can also do a less selective alkylation or acylation by doing, basically, this is an example here on the right side called the Williamson ether synthesis. Okay, we like to use silver salts here because this produces as a byproduct AgBr, and this precipitates out of solution, so that's a very favorable process there. Okay, I'm just showing in these two equations here with methyl iodide and benzyl bromide, just using large excesses of base in these reagents, and we're turning all of the OH groups into ether groups. So here they're all benzyl groups, here they're all methyl groups. Okay? All right, now once they're here, we can actually do an acetal hydrolysis and selectively remove only the anomeric OH group. Okay, so here only the anomeric OH group is converted back into an ether. And remember that because that is an acetal, it's much easier to hydrolyze than the others. The others are just simple ethers. Remember back in the ether chapter, ethers require extremely strong acids. Here just H3O plus at a pH of about 1 or something like that will actually cause the hydrolysis to occur quite effectively. All right, I'm just showing here the exhaustive, what we call the exhaustive alkylation, where we're alkylating all of them. There are very specific recipes worked out where you can hydrolyze just some of them, or alkylate some of them, but we're not going to really go through that in this class. That would be a class totally devoted to carbohydrate chemistry. We just don't have the time to discuss all the possible ways you can alkylate. There are many different recipes. We're just showing you the exhaustive alkylation. All right, over here we have the exhaustive acylation. Okay, we're basically exposing this to conditions for making an ester formation conditions. Okay, so these are conditions ideally for converting an alcohol into the corresponding ester. All right, so if we treat this carbohydrate mannose in this case with a large excess of benzoyl chloride, the acid chloride here in pyridine, what we're going to find is that we get benzoate groups on every, or benzoyl groups on every oxygen. Okay. Here's an important thing to remember, and that this is abbreviated BZ, and that benzyl is abbreviated BN. So BN versus BZ, that's the distinction there. Okay, and I think that's it for reactions. We're just going to try to complete a couple of reaction equations here. So we're going to predict the product of each reaction. All right, so we're going to take the first one. We're going to treat it first with ethanol acid and then aqueous methanol silver oxide. All right, so step one is going to basically be totally selective, occurring only here. And so we're going to make this compound here. We're going to put an ethyl group at the anomeric carbon, and we're going to put methyl groups at all of the other carbons. Okay, In the second reaction, we're just doing the Fischer-Killani chain extension. Here we have an aldopentose. This one, I believe, is actually arabinose. Now we're going to we're just going to do the Fischer-Killani chain extension on this, okay? All right, so what we're going to find here is that we produce two new carbohydrate systems. We produce glucose and mannose on the left. The new carbohydrate, their new stereocenter that I've put an asterisk at, we have no control, so we're producing both. All right, so this is how the structure of glucose was established in the 19th century by how it is derived from arabinose, okay? And arabinose is derived from erythrose, okay? So Fischer did a lot with very few tools at his disposal. The fact that he could assign all these chiral centers in the 19th century with no spectral tools available to him is really amazing. All right, so we'll now stop here, but in the next video we'll look at disaccharides and we'll look at carbohydrate metabolism. Okay?